Hi, this is Sir Aris. Let us talk about techniques for obtaining power series expansions, accuracy of series approximations, and also some uses of series. So we can combine different techniques in order to get um, power series for different functions. Um, we also will be making use of popular functions whose series are can be easily obtained and you can also memorize. Uh, for example, sine x. So it's just x minus x cubed over 3 factorial plus x5 over 5 factorial and so on. It's conversion for all x. Cosine x, it's a little bit different. So you have even powers with alternating signs. EX, this one is very easy to memorize. This should be something that you should know. Uh, Whenever I come across you in the department, if I ask you what is the series for exponential EX, you should be able to answer me directly that it's 1 plus x squared over 2 factorial plus x3 over 3 factorial, and so on. For ln 1 over 1 plus x, this is the series, but it's convergent only for x between minus 1 and 1, not including minus 1 and 1. 1 plus x to the power of p, you have this binomial expansion where this coefficients is convergent only for x between minus 1 and 1, including the, no, not including minus 1 and 1. Now let's consider the techniques. We have multiplying a series by a polynomial or by another series. So for example, x plus 1 times sine of x. So what we need is just the sine of x, and then we multiply each term um, by a by x plus 1. So we know that sine of x, okay, sine of x can be written as, so if you look up here, x plus or minus x cubed over 3 factorial plus x fifth over 5 factorial minus x seventh over 7 factorial, and so on. Okay. Now, if you multiply this with x plus 1, this becomes, so this term, okay, times 1 times this x plus that term again times x. So we have, say we multiply first with x. So you have x squared minus x fourth over 4 factorial. Okay, so what I'm writing here, let me just be clear. I'm writing x times sine of x plus sine of x. Okay, let me write x and sine of x first. So that's x squared minus x to the power of 4 over 3 factorial plus x to the power of 6 over 5 factorial minus x to the power of 8 factorial, and so on, plus the original terms x minus x cubed over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, and so on. Okay, which means that we can write this simply as we start with x, the lowest one with lowest power, plus x squared minus x 3 over 3 factorial minus x4 over 3 factorial, and so on. So that's our x plus 1 times sine of x. Okay, very easy as long as we know what is sine of x. Okay, now how about if we divide two series by a series or a polynomial? So let's choose a simple one, just divide it with polynomial x. So we have ln 1 plus x. So given this ln of 1 plus x, we can just write 1 over x ln of 1 plus x as sum the series of ln of 1 plus x, which is this, divided by x. So that becomes 1 minus x over 2 plus x squared over 3 minus x 3 over 4, and so on. That's very easy. Okay. Another case, you have a binomial series. We can make use of the binomial expansion uh, to solve the to expand function. So let's say you have a function of this form: 1 plus 1 over 1 plus x. You can write it as 1 plus x to the power of minus 1. So that's here same as this, but with p equals minus 1. So when p equals minus 1, you have here minus 1, 0, that's 1. Here minus 1, 1, that would be minus 1. Here minus 1, 2, that would be minus 1 times minus 1 minus 1 over 2 factorial. That's 1, or minus 1 actually. Okay, this is a minus. No, no, this is plus. Okay, minus times minus is plus. So you have minus 1, 3. That would give you minus 1 times minus 1 minus 1 times minus 1 minus 2 over 3 factorial. That's minus times minus minus 1. And this is 3, this is 2, this is 1, that's 3 factorial. Factors out. Okay, generally, so here we can write this as so the term xn, so x to the power of 0, so 1 times x to the power of 0 plus negative 1 to the power of x to the power of 1 plus 1 times x to the power of 2, so here, plus negative 1 x to the power of 3, and so on. And there's actually a pattern here. If it's odd numbers, you have positive 1. If it's even, you have negative 1. So we can write it as sum of all uh, minus x to the power of n, if we start from n from 0 to infinity. So that's our 1 over 1 plus x. Okay. Now, how about if we substitute a polynomial or a series for the variable in another series? So, for example, this one. So we have x squared, simple polynomial. If you use this known expression for ex, you can write e to the minus x squared as ex, but x replaced by minus x squared. So we have 1 plus negative x squared squared over 2 factorial plus negative x squared 3 over 3 factorial plus negative x squared to the power of 4 over 4 factorial, and so on. Or we can write it as e to the minus x squared as 1 plus x fourth over 2 factorial minus x6 over 3 factorial plus x8 over 4 factorial, and so on. Okay, what else? You have combination of methods. Suppose we use the series for arctangent. Arctangent, we know we can write it as an integral of dt over 1 plus t squared from 0 to x. Now, if you have, we go back to this binomial expression we derived, or binomial expansion with p equals minus 1. Now, if you have 1 plus t squared to the power of minus 1, simply substitute x with t squared. So you have 1 minus t squared plus t squared to the power of 2 minus t cubed to the power of 3. No, that not t cubed. T squared to the power of 3 and so on. Okay, so 1 over 1 plus t squared is 1 minus t squared plus t fourth minus t6 and so on. Now if we take the integral of 1 over 1 plus t squared dt, um, we can just take the integral term by term. So you have integral of 1 minus t squared plus t fourth minus t6 and so on dt from 0 to x. Okay, so this, integrate this, that becomes t. So from 0 to x, that's x. This t squared becomes t to the power of 3 divided by 3. So that's x3 over 3. So here x4, that's x5 or t4, that's x5 over 5. Minus here x7 over 7. And it can go on. So our arctangent, which we write like that, has a series expansion given by this. Okay. Another one, when Taylor series can be expressed using basic Maclaurin series. For example, we want to know Taylor series of ln x about x equals 1. So if we do this by our definition for Taylor series, it will take, it doesn't take that much of time, but it is a long process. It is easy if we take the Taylor series about x equals 0, that's the Maclaurin series. Here we can do that, but we replace our ln x by ln of 1 plus x minus 1. Okay, essentially we add 0, so 1 plus 1 minus 1, that's 0, but we take this as one term, so 1 plus x minus 1. Okay, so taking so writing it like this, we can just use our series expansion ln 1 plus x, and we substitute our x here with x minus 1. So that becomes x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 fourth over 4 and so on. So that's your ln x expanded about x minus 1. So this is about x equals, not x minus 1, but x equal to 1. Okay. There are also other methods, but for now, let's proceed to accuracy of series approximations. We know the definition of remainder, but for our Taylor series, it's the difference between the value of the function and the sum of n plus 1 terms of the series. So you have Rn equals the function minus these terms. If the series converges, that means that the function uh, would be, so for the function, if the series converges, it means that the limit of this Rn goes to 0. Now, suppose we know the power series and it converges, and but we want to use only an approximation. If the series is alternating and it converges, we can estimate the error caused by using only a few terms of the series. We use this theorem. So if this is the alternating series, uh, it's decreasing, so an plus 1 is less than an, the absolute value is decreasing, and the limit goes to 0, then s minus um, this first n terms is less than or equal to an plus 1. What it means is that the error, if you approximate, is less than the absolute value of the first neglected term. For example, if you have this alternating harmonic series, the sum of this series is known as 2/3, but so this is equal to 0.666. If we only add only up to 1 over 32, say we neglect the terms 1 over 64 and above, we get 0.656. Subtracted from 0.666, we get 0.01. 0.01, if we solve for 1 over 64, that is 0.015. So our error is, or in this case, it's 0.01. It's always less than than the absolute value of the next term, which is, in this case, 0.015. Another theorem, so if you have S in power series form, converges for absolute value of x less than 1, and it's decreasing in absolute value for n greater than some value capital letter N, then S minus that series up to capital letter N is less than a n plus 1 x to the n plus 1 divided by 1 minus absolute value of x. Okay, series is very useful. We can use it for numerical computation. For example, uh, if you want to solve the value of a series and you know the tricks, you can easily find the numerical value even without using more advanced methods like using a computer. You can also get the sum of the series, knowing all this knowledge on series. If you take integrals, there are methods that we know so that we can easily get the integrals using, suppose we expand the function in series form and then we take the integral. It's also useful in evaluating indeterminate forms, because sometimes if the function has an indeterminate form and you take the limit, you can always take um, the series expansion and hope that it would cancel out certain terms that make it indeterminate. And also, of course, you can use series for approximations.